implications and what's been done with that data, how the results have been interpreted, and the impact of that study on national guidelines and standards, and also on the practice of occupational medicine. And I think I'm going to conclude with and touch on where this all starts from, and that is mining, and how this kind of research can impact industrial ergonomics and industrial medicine. Most of the research we do in my lab started off really in the office ergonomics arena. Our lab did a lot of work on office design, office ergonomics, computer mice, keyboards, and so on. And we're shifting now into new technologies like gesture, virtual reality, and augmented reality research. But that's a big complement to the kind of stuff I'm going to talk about today, which is more industrial ergonomics and industrial occupational medicine. But I'd be happy to talk with any of you afterwards about ergonomic implications of AR and VR, which we're all going to be experiencing in the next 10 and 20 years. So this is what I'm going to talk about is a nationwide prospective study. But the reason for this and what motivates research in musculoskeletal disorders is that our companies in the United States spend a tremendous amount of money on occupational injury and illness for disability payments, for lost work, and our workers pay for that too. If you look at the latest national data, this is detailed analysis by Paul Lee at the University of California at Davis. He's an economist, and he looked at all data in the country where he could find costs related to occupational injury and illness. And in 2007, the blue columns, the cost of this country for direct and indirect costs were around $250 billion. A majority of this is related to musculoskeletal disorders and injuries. And that's comparable to our national cost for circulatory diseases, strokes, heart attacks, et cetera, and our national cost for all cancer. And yet the amount of research money spent on our field for the prevention, and I believe that all of these are preventable, or almost all of them, is relatively small compared to the other disorders that we deal with in the National Institutes of Health. So that and other factors motivated Congress about 16 years ago to fund the National Academy of Sciences investigation on what exactly is the data showing a relationship between work and musculoskeletal disorders. The National Academy of Sciences did a 2-year study and published this book called Musculoskeletal Disorders and the Workplace to address the questions, and they concluded that really the federal government should fund research to quantify the relationship between exposures and outcomes for musculoskeletal disorders. And that conclusion then led NIOSH to set aside $12 million for what's called the Big Ergo Studies. This university has received a fair amount of money as part of this agreement, and the purpose was to fund large prospective studies on low back pain and upper extremity disorders to try to clarify work and non-work factors related to these disorders. And really to dig into this question right here for upper extremities, what are the relative contributions of repetition, hand-wrist exertions per minute, pinch and grip force, wrist postures, psychosocial factors, non-occupational factors, and what are the dose-response relationships between those factors and musculoskeletal disorders? Without a clear understanding of the dose-response relationships, it's very difficult for industry and regulators to set a standard and provide good guidelines for what should be reduced and what shouldn't be reduced. All of us know that motions, force, posture, and even psychosocial factors are an important part of normal life and normal work. It's not like lead and other toxic chemicals where we don't need that exposure. We need all of these exposures to live. But how much exposure is too much exposure, and how much exposure is reasonable? And that was the purpose of this study. So these are the study sites around the US that independently set up research projects to evaluate prospectively these endpoints. And at the end of their data collection, we ended up pooling the data from all those sites. And by pooling all that data, we wound up with 4,321 workers followed prospectively for up to 6 or 7 years. 55 different enterprises were involved in here, ranging from production, agriculture, healthcare, work. So the results, this is probably the largest workplace study, at least in the US, evaluating musculoskeletal disorders, of the longest duration and of the broadest set of industries. So the results are relatively generalizable. We focused on carpal tunnel syndrome, which is what I'm going to be talking about this morning, but also other disorders, tendinitis, epicondylitis, rotator cuff disorders. And so far, there have been more than 25 publications from this research from the individual groups. And for the pooled data, we have 14 publications now demonstrating the results. And that's what I'm going to be talking about here. I think all of you are familiar with carpal tunnel syndrome. I'm not going to spend much time except to say that it involves a compression of the median nerve at the wrist as the nerve passes through the tunnel and is compressed just below the flexor retinaculum. The condition can be characterized clinically by a certain set of symptoms, and those specifically are numbness, burning, tingling, or pain in the thumb, index, or long fingers, and a positive electrodiagnostic study. So those are the criteria we used for case outcome in this study also. We collected other data, which you'd expect in a study like this. All the sites collected demographic information, medical health history, recreational activities, non-work activities, and psychosocial stress measures at the work. I think all of you are familiar with the job strain index, something called the job content questionnaire is used to develop this index, where jobs are divided into low demand, high demand jobs, low control, and high control jobs. And then from that, classified into these different quadrants. So, for example, your jobs would fall where on this category? All of you have high control. You're here. You have control of your life, generally. And you don't have a minute-by-minute control by some other source. So you have a high control. And probably, I'm in the low-demand job because I'm retired now. But I used to be in this high-demand setting over here. So this is where most professionals wind up in terms of exposure. A low-control, high-demand job might be an assembly line job. You can think about what's a low-control, low-demand job? Anyone think of one like that? It might be a receptionist, maybe security guard, those kind of jobs where you have to pay attention, but there's not that minute-by-minute surveillance and observation of what you're doing. Anyway, we're going to come back to this in terms of the findings. This is a classic way of evaluating psychosocial stress in the work, along with social support. So this would be social support from coworkers and supervisor, which is a different kind of classification. Probably the most important factor in our analysis was the detailed biomechanical exposure variables that were measured. Force, repetition, posture, percent time doing things with the hands, combination of percent time and force, and combination of repetition and force. Force was estimated by both the worker and the analyst on a subjective scale called the Borg scale from 0 to 10. Repetition, same. These other measures down here were estimated from a video analysis primarily, where analysts looked at videos and they were blinded to health outcome. So they didn't know when they were looking at someone doing the job whether that person had a health problem or not. So there was good blinding in terms of the exposure assessment. And it's a relatively objective way of assessing posture, percent time doing things with the hands, and measuring repetition rate. And I can talk about the details of that later if you'd like. From this video analysis, in my lab, I had 6 undergraduate students looking at these videos frame by frame, doing an analysis of every frame and what the hands were doing at every frame's point. For example, in this case, the right hand is doing nothing, so it would be no load. The left hand here is gripping a platform and moving materials, so it would be classified either as a light grip or a heavy grip, or a light pinch or a heavy pinch. Pinch or power grip, depending on how the force is distributed in the hand. I think you are all familiar with the power grip, gripping like a shovel. Pinch grip would be force is just transmitted between the thumb and either the index or thumb and the middle finger, and the force isn't transmitted to the palm. And the important reason for differentiating between pinch grip and power grip is that if you measure the force in the tendons of the forearm and apply an equal force at the fingertips, the tendon force is much higher with a pinch force than a power grip. So an equivalent pinch force in terms of force is a greater risk than equivalent power grip. And that's why for the threshold here, for a heavy pinch, we used a 2-pound force threshold, 1 kilogram or 10 Newton. And for the heavy grip, we used a 10-pound force threshold for classification. This is going to come back and be very important later on in terms of practical implications. The statistical analysis were relatively conventional. We used predictors of incident, that is, new cases of carpal tunnel syndrome in the study. Anyone who had carpal tunnel syndrome going into the study was excluded from the analysis. We're only looking for new cases in this follow-up period. The standard Cox proportional hazard model was used, similar to maybe the odds ratio, relative risk in terms of considerations. And all the measures and analysis were adjusted for age, gender, BMI, the research study site, and non-overlapping biomechanical exposures. What we mean by non-overlapping is that if we're measuring repetition rate of the hands and then also measuring forceful repetition rate, there is some overlap in those two measures. There is a correlation between those measures. So we didn't include both forceful repetition and all repetition rates in the same biomechanical model. These are the results. I'm going to show you the results first for the personal factors, and then the psychosocial factors, and then the biomechanical factors. And so, first of all, there's 204 new cases of carpal tunnel syndrome in this follow-up period, giving an incident rate of 2.3 cases per 100 person years in the study. We had about 5,000 or 6,000 person years of follow-up in this research. Gender was an independent risk factor, hazard ratio of 1.3. You can see that it crosses 1.0, meaning that it's borderline not significant. Probably the p-value here is about 0.06 or 0.07. Body mass index, obesity, about a third of the population had a weight of more than 30, and body mass index had an elevated hazard ratio of 1.7, which was significant. Interestingly, the comorbidities of diabetes, rheumatoid arthritis, gout, and thyroid, the hazard ratio was not elevated. Surprise. Any idea about why might that be the case? For two reasons. It's because it's something I didn't tell you. And one is that we basically excluded people with carpal tunnel syndrome at baseline. And these people probably may have had carpal tunnel syndrome going into the study. The second is we excluded people from the study who had a polyneuropathy. So if they had an ulnar, a prolonged ulnar latency at the wrist, we excluded them too. Wasn't that many, but those people are likely the ones that may have had a diabetic-related polyneuropathy. Interestingly, non-occupational hand activity, and this would be things like knitting, gardening, housework, more than 3 hours per week. The hazard ratio is less than 1. That means that that was protective in this prospective study. Doing these activities, knitting, gardening, housework, hand-intensive, which we think as contributors to carpal tunnel syndrome, was protective. This was surprising to us. The other is that non-occupational aerobic activities, jogging, swimming, basketball, soccer, walking, slightly protective, but not significant. In terms of the psychosocial factors in the study, we found, as you might expect, that the high demand, low control job, this kind of assembly line job, high strain job, had the highest hazard ratio, which was significantly elevated. The other quadrants, the active and the passive quadrants, were slightly elevated, but they were not significant. Having high support from coworkers and supervisors was very protective. And you can consider this as basically supervisors and coworkers considering other employees that have symptoms and maybe filling in for them or making adjustments for those coworkers, for those workers, or there may be other relationships here in terms of how to interpret that. Job satisfaction, basically dissatisfied with the job, was slightly elevated, but that was not significant. Okay, here we get into the crux of the findings, the biomechanical findings. And the way we interpret these is we're looking at two different factors, factor above the line, one factor here and one factor here. They're separated by this line. And the hazard ratio of 1.0, hazard ratio of 2. So if the central tendency is right on the 1.0, there's really no increase in risk or decrease in risk relative to the control group. So this first one up here is wrist posture, the percent time with the wrist in more than 30 degrees of extension. And here, the percent time with more than 30 degrees of flexion. And you can see that increased time with the wrist in more than 30 degrees of extension did not increase your risk for carpal tunnel syndrome. So in this production-based population, who typically don't have a sustained non-neutral wrist posture, their wrist postures are moving all over the place during this activity, unlike computer work, they did not, there was no increase in risk with increased wrist extension or wrist flexion. In terms of looking at peak hand force, either estimated by the worker or estimated by the analyst, there was an increased risk. This is an estimate from 0 to 10, increasing peak force estimated by the worker and increased peak force estimated by the analyst showed a dose-response increase in risk for carpal tunnel syndrome. Very interesting findings for hand repetition rate. Probably the most interesting findings in the whole study. And that is, if you look at the HAL scale, and all of you were introduced to the HAL scale, I think, yesterday, as part of the hand activity level TLV. It's an estimate of hand exertion or repetition rate. There was an increased risk, but it was not a dose-response increase in risk with a HAL scale. And above 5.0 on the scale, it seemed to come down. If you look at the video analysis data, here these values are less than 13 exertions per minute, 13 to 26 exertions per minute, more than 26 exertions per minute, measuring all exertions of the hand. This would be the wrist moving in extension, flexion, pinching, gripping, any kind of exertion like that is counted as an exertion or repetition here. That there's no increase in risk with increasing repetition rate. For me, this is the most unexpected finding in the whole study. That repetition per se, repetition exertions did not increase the risk for carpal tunnel syndrome. But when you isolate and just look at the repetitions and exertions which are forceful, where simultaneously the hand was pinching an object or gripping an object at high force, using these force thresholds I talked about before, more than 2 pounds of pinch force or more than 10 pounds of power grip, there was a dose-response increase in risk with carpal tunnel syndrome. So going from less than 2.6 exertions per minute, you begin to see an elevation between 2.6 and 9.6 exertions per minute, and more than 9.6 exertions per minute, there's a clear increase in risk. So here, this begins to provide some dose-response information about biomechanical exposures and risk for carpal tunnel syndrome. Duty cycle. Duty cycle is a different way of looking at how the hands are active at work than repetition rate. There's an overlap between duty cycle and repetition rate. They're not identical, but there are some similarities between the two. And duty cycle is really just a measure of the percentage of time during the job that the hand is applying, in this case, a forceful pinch or a forceful grip. So I showed you before the person on the video gripping a handle on a trolley. And so the left hand was gripping, so there would be the duty cycle on. The right hand is not gripping anything, duty cycle off. So that's the measure of the percent time the hand is touching something or exerting a forceful exertion. So interestingly, if you look at the duty cycle for all hand activities, so anytime the hand is touching anything, if the hand is resting on a surface like this, if the hand is gripping something like this, or if the hand is gripping a high force exertion, there was no increase in risk. Parallels the finding with the repetition rate. But if you isolate now the duty cycle to only forceful hand exertions, forceful pinching and forceful gripping, a nice dose-response increase in risk with carpal tunnel syndrome. Duty cycle. So duty cycle, percent time in forceful pinch or grip. You can look at this kind of pattern, stylized pattern up here. Duty cycle is an electronics engineering term. It comes from current passing through circuits, but we apply it here simply as the percent time that the hand is exerting a force on a tool or an object. 10% duty cycle, 50% duty cycle, 90% duty cycle. Same repetition rates, but if you were doing this job, which one would you want to do? You'd probably want to do the 10% duty cycle, not the 90% duty cycle. And sure enough, the duty cycle in this case, the 90% duty cycle is clearly a higher risk than the 10% duty cycle. And yet, we have the same repetition rates. I think the correlation coefficient in our data set between repetition rate and duty cycle was about 0.57. So there is some correlation, but it's not a high correlation. It's a moderate correlation between the two. And therefore, it's in some cases difficult to put them in the same model. You might be over-controlling for one compared to the other. So in terms of the conclusions from these findings and clinical applications, workers exposed to a high force grip and or a pinch are at increased risk for carpal tunnel syndrome with a peak force of more than 3 on the CR10 scale. If the repetitive forceful exertions are more than 3 forceful exertions per minute, or if the duty cycle sustained force is more than 11% of the time. This is probably the most important take home right here. We're beginning to see now a line in the sand, a threshold to consider for evaluating a job and when that job is at high risk and when that job is at low risk. High psychological demand may increase risk of carpal tunnel syndrome, particularly among those with high biomechanical exposure. Decision latitude, social support were protective when the biomechanical exposures were low. This is the table from the ACGIH TLV on hand activity level, which you saw yesterday if you were here for the meeting. And this is the current, this has been in place, I think, for about 10 years in the ACGIH TLV. And the way this is interpreted, the hand activity level or the measure of exertion rates goes up, or the normalized peak force goes up. You can move into this unacceptable zone for work. As it goes down in repetition rate and down in peak force, you move into this zone down here. The data findings from our study and also from a study, a somewhat similar study from Italy, demonstrate that even in this high acceptable zone here, we're seeing cases with carpal tunnel syndrome. And probably, if we were going to readjust these threshold lines to correlate with the data from our data set, we would adjust these threshold lines down at this end and maybe make them a little flatter. So they look like this. So the first impact that our study is going to have on a national level is a modification of this threshold lines. Next week, our Physical Agents Committee at the ACGIH is meeting, and we're going to discuss a recommendation to bring this point down to 5 and bring this point down to 3, modifying the threshold values for what's in the unacceptable and the acceptable range. There are lots of other tools that are useful for assessing risk for musculoskeletal disorders. I just mentioned the hand activity level. There's a strain index, which many of you are familiar with. OCRA, Occupational Repetitive Actions, is a method out of Italy. RULA out of Scandinavia. There are general musculoskeletal risk assessment tools, risk assessment tools for lifting, and risk assessment tools for psychosocial stress. All these are on our International Ergonomics Association website, including links to these sites for these risk tools. They're also listed in detail on this site from Finland and the site from Tom Bernard's from Florida, if you're interested. I think these slides will be available to everyone in the group. Kurt, is that right?
I think so, yes.
Yeah, so you don't have to write this all down now. Somehow you'll make the slides available to everyone here if they want to. So if we look at just one of these risk assessment tools, the psychophysics tool. Has anyone here ever used psychophysics tools? Okay, psychophysics tools are an interesting kind of subjective method of determining whether a person can accomplish a job or not. And these psychosocial tools in this particular table has been used to basically set the limit for baggage weights in Europe for airplane flight. So when you check your bag in Europe and you check your bag in, there's a limit on what that bag can weigh for one person to handle it versus 2 people to handle it. And that limit is based on psychophysics tables. And a lot of companies use psychophysics tables because there's no other place to go to with these kind of details in terms of the threshold for how much to list and not list. So this particular table, maximum acceptable push forces for females based on the height of the push point, the percentile of the population you're trying to accommodate. Are you trying to accommodate 90% of the population or 10? Or what they can do? This is a 2-meter push every 6 seconds, 1 minute, 2 minutes, 30 minutes, and so on. So this is really a detailed table. If you go down here, then you can say, well, at this point, a push every 30 minutes, the limit at that height is going to be 30 kilograms. Detailed table to go to for both pushing and pulling, lifting, lowering. There's a lot of tables like this developed by Stover Snook at Liberty Mutual Insurance Company. These psychophysics tables are developed by bringing in 10 or 100 people into a laboratory and having them do a lifting task over and over again for an hour or 2 with different weights at different rates, and asking them, could you do this job all day long without developing too much fatigue? Would you be, could you do this job at this rate? And so it's subjective, but it's a large number of people, so you're kind of smoothing out the data. It's an important data set. Jim Potvin took all of the psychophysics data for upper extremity exertions. So there's both lifting, lowering data, but there's also very detailed data having people sit with their hands in front of them and exert a force over and over and over again 8 hours a day, and adjust the force they're pushing at a certain rate to a level of force that they can handle all day long. Same kind of concept, psychophysics. And so Jim took the 12 psychophysics studies in the literature on upper extremity and plotted them out as repetition rate, exertions per minute, and maximum acceptable effort based on your strength. And there's kind of this nice distribution here. Higher the repetition rates, the lower the maximum acceptable effort, as you'd expect. But there's a pretty big distribution here. It's a big spread. When Jim then replotted this, instead of plotting on this lower axis repetition rate, plotting a duty cycle, it's much tighter. So based on the psychophysics data, we'd say that maybe duty cycle, rather than repetition rate, and maximum acceptable effort is a better way of understanding fatigue and what a person is capable of doing at the workplace. And this is the basis for, just published last year, the ACGIH Fatigue TLV. If none of you are familiar with it, you should look in your little ACGIH booklet in the physical agent section. This is a brand new TLV that just appeared last year for the first time. And based on the Jim Potvin curve, this is a little different curve than the Jim Potvin curve, but it's the same kind of concept of what's tolerable and what's not tolerable. And it's a nonlinear curve. The other take-home message now, I'm going to give examples of case studies from our group in terms of how to apply what we found here with real workplaces. So the main message that I'm taking home from this research is we want to reduce the pinch force and the grip force to levels below the thresholds we identified in our study, below 2 pounds of pinch, below 10 pounds of power grip, especially if they occur repetitively, and try to either reduce the force levels or reduce the duty cycle. And this is a case study of an example from the utilities industry, high force job. Utilities workers have to cut big cable, usually aluminum, sometimes copper cable that's 1 inch or 2 in diameter. This is hard work. High force. How would you modify that job? Longer handles? Maybe make the handles about 20 feet long? Ratchet? So you use a tool with a ratchet and then your ratcheting mechanism so you get a leverage. The industry, so 15 years ago, the utilities industry, spent $1 million trying to solve this problem. And this is the solution they came up with. Powered crimpers and powered cutters. These battery-powered crimpers and battery-powered cutters are now in almost every utility truck, having replaced those long loppers. Each of these devices cost $1,000, but just think of what they're reducing in terms of the kind of forces applied and the risk both for injury and musculoskeletal disorder. An important engineering intervention based on reducing these high force activities in the workplace. When you talk to electricians in the workplace, there are two jobs they hate the most. One is wire pulling. They hate wire pulling. And you have to pull this wire through conduit, usually to a circuit breaker box. And depending on how many turns the conduit does, the diameter of the conduit, the size of the wires, pull force can be very high. So you reduce the pull force by putting a lubricant in the conduit, having not too many turns in the conduit, so you have pull boxes at different places. Or you can use a conduit pulling system like this to reduce the pull force. This is reasonable to use if you have to pull a lot of conduit, for example, into a circuit breaker box. But this is bolted to the floor here, so you wouldn't want to do this for every conduit you pull. But if you have to pull a lot of conduit, something like this is reasonable. And these pullers exist for small wire like this and for huge wire like the big 1 inch diameter wire too. The other thing that the electricians hate to do is drill into concrete overhead. And I'll talk about some interventions for that in a bit. This is a job we investigated in Southern California at a nursery. These women working on the lines are cutting twigs, and it's for basically developing rootstock. They have to cut a twig and insert another root stock into that. And they're doing all the cutting of these twigs with a electrical cutter. And 3 of the 5 women on the line developed carpal tunnel syndrome. We do this over and over. They do about 1 every second in the cutting. And this tool pushes right in the palm, right in the middle of the palm, next to the median nerve. The intervention here was developed by the University of California at Davis, their agricultural center, and was a powered cutter, air-powered cutter. And basically now they just take the twig and they guide it into the cutter. It cuts it automatically and they pull it out. So they can actually do more cutting than they could before with no risk, high force risk, and no fatigue. Davis built about 1,000 of these units, and they're distributed throughout California at different nurseries to replace this task that was done before by hand. Engineering intervention to reduce the high force cutting. This is a biotech job that I worked on with something called the Joint Genome Institute, run by the Department of Energy in Walnut Creek. The Joint Genome Institute does DNA analysis. They did a lot of the DNA analysis for analyzing the human genome, and they're doing DNA analysis now for analyzing genomes from almost every creature in the world. And this involves 96 well plates, where the fluid is placed in plates and mixed, and then those plates are sealed with this aluminum sealer, and then it goes into a PCR machine for temperature changing in order to ultimately do the DNA sampling. And the workers on this, what became an assembly line-like job, had to peel the aluminum foil off the 96 well plates, every one of them by hand. As it became more and more a production demand job, this became the bottleneck. This is the job that caused wrist pain. This is the job that caused pinch, forearm pain, and the job that caused injuries among these biotech workers. And we tried all sorts of things. What would you do to make this job easier? Well, if you're thinking about it from a systems perspective, you say, well, why bother putting aluminum on the surface in the first place? Isn't there a better way to seal this so you don't have to peel it off like that? Or isn't there a better way to do this job so it's not so manual? Maybe automating the whole thing, which was not available at that time. It is now, but it wasn't at the time when we did this investigation. Someone recommended, well, maybe they should just pull this off with tweezers instead of their fingers. Is that going to make any difference? No. Same force. We tried lots of things in terms of reducing the impact of this. Ultimately, the only thing that was effective was a $30,000 intervention. Basically, we developed a custom-made machine that you slide these 96 well plates in, and the machine peels off the aluminum for you. An engineering intervention just to get rid of that job altogether, and the workers can focus on other kinds of job, automating this particular task and stripping the aluminum foil off. It's a custom machine, and now it's being used at other sites too. And in terms of case studies, I'm going to conclude with the drilling project. This is the job I mentioned that electricians, plumbers, sheet metal workers, pipe fitters hate, one of the ones they hate the most. You're drilling, the drill weighs anywhere from 2 to 4 kilograms. You're applying an upward force about 25 kilograms. So basically it's like holding a 50-pound weight over your head while it's vibrating, pushing up, dust falling in your face, noisy, risk of falling from the ladder. There's a risk here for her besides just the hand forces involved, shoulder loads. And over a 5-year period, we investigated alternatives for doing this job in a participatory process with electricians and plumbers and pipe fitters. Ultimately, we came to a solution, an engineering solution, that involved this rig right here. It basically is like an inverted drill press. The drill is mounted on top of the column in a saddle. This column then is pushed up to the ceiling while the drill is active with this wheel, and it drives the drill then into the ceiling. The worker can stand on the floor. They can move this from one hole to the other, and the amount of force they apply now is 25 newtons or 2.5 kilograms, instead of 25 kilograms for the job. So less force, no fall risk. They do have to look up at the ceiling a little bit, so there's some neck extension issues, but we've been dealing with that. And this kind of intervention works when you have to do a lot of holes. If you have to do just a few holes, don't bother. But if you have to do something like 30 to 100 to 200 holes, then this may be useful. And that's when this is used. This thing we developed about 7 years ago has been commercialized by a company in North Dakota called TelPro. They made it even better than the one we developed, cheaper. And this is their product that they're selling. We don't have any IP on this product, so they're welcome to go and do whatever they want. And so it's the same kind of concept, but you can see here the drill's extended pretty high with this system, and it costs about $1,200. And they're selling it now out of this company in North Dakota. TelPro, by the way, is the same company. I don't know if you've seen it, but they make a device that lifts sheetrock up to the ceiling through this kind of system. So it fits in with their product line. We've gone on now to try to tackle a bigger drilling problem. This is big scale drilling 1-inch diameter holes, 1 foot, 2 feet into concrete, and it's used for structural upgrades. Over the Bay Area, we have to worry about structural upgrades for earthquake. Maybe you don't have to worry about that here so much. But 125 decibels of noise. This is essentially a jackhammer being handled by hand. These weigh about 20 to 45 pounds each without the bit. You have a hose here. The vibrations are some of the highest vibrations you've ever measured, silica dust exposure, and high risk for musculoskeletal disorders. So we essentially tried to apply the same kind of concept with the participatory process with these construction workers to develop something better. This, by the way, is the BART tunnel, the train tracks which go overhead all over the Bay Area. And each of these columns had to be upgraded with the addition of concrete around all the columns. And each column, they had to drill about 700 holes with the insertion of rebar. So I tried doing this myself, and I can handle about 3 or 4 holes before I'm fatigued. And the workers who are pretty strong, they can do this for about 2 hours. But they can't do this all day long. It's really too fatiguing. There's a sound wall built in Marin County that required 20,000 of these holes. There was a building we worked on in San Francisco that required 80,000 of these holes for structural upgrades. We're talking about, not just a few holes, but thousands and thousands of holes that are being drilled. And the intervention that we developed looked like this. Same kind of concept as you saw before. Basically, the drills are in a saddle on the end of a column. This column then is rotated out with this linear gear, and it reduces the force, much less hand vibration. In this case, we have 2 drills on here because what we're doing is drilling 2 holes simultaneously in order to put on a clamp for a pipe. And so the holes have to be aligned, and this saves time, and the alignment's very easy with the 2 holes drilled. We developed this one for putting in a 6-inch conduit through the whole BART tunnel that goes underneath the bay from Oakland to San Francisco. And the workers could only work from 2 o'clock in the morning until 4 o'clock in the morning. Otherwise, the tunnel is being used. And so we had to come in, you have a short time of doing the drilling overhead for putting the holes in, and then they're out. And this helped basically meet the productivity expectations of when they would get the job done and help decrease the time of the job, and they could finish it in time. We are now about to embark on mining, tunneling, and drilling investigations through a grant from NIOSH and something called the Alpha Foundation. And I don't know if any of you are familiar with something called the jackleg drill. Any of you here? This is a crazy tool. This is a wild tool. It is the most common tool used by miners in hard rock mines because it's so versatile. And it's for drilling 1-inch diameter holes up to 10 feet into the rock for planting explosives, for drilling enough holes to basically remove rock, for gold mining, silver mining, also others, coal. And this whole thing weighs about 150 pounds altogether, and it's handled manually. So you've got a pneumatic drill, a steel here that's anywhere from 4 to 16 feet long. We're drilling the hole. And then this leg right here, which is a pneumatic leg. So you're holding this thing up. It's vibrating, tips bouncing all over the place. You have to get it started. Once you get it started and in about a foot or two, then you can let this pneumatic leg drive it in the rest of the way. But until you get it started, you're basically handling not only the whole weight of this thing, but it's jumping all around. You're trying to get it stabilized. And then when you have to pull it out to change the steel to a longer bit or to move to a new hole, then you have to again handle it manually to the next hole. This tool causes more musculoskeletal injuries than any other tool in mining. And we're trying to then work with the miners and figuring out how to modify that tool using some of the same concepts we developed with the construction sector without impacting the versatility of this tool. This is such a versatile tool. You can move it from one place to another really easily. And we don't want to reduce that versatility, but we want to also reduce the kind of loads that are being handled and reduce the possibility for injuries to the workers. So I'm going to conclude with this slide, and it's the recommendations from a paper by Jan Doel, who is an ergonomist and also an MBA. He works at a business school, and his whole focus is on trying to promote ergonomics in the business community. Not in the engineering community, not in occupational health. He focuses totally on business schools. And his paper and the suggestions from Jan Doel and others, this is a really important paper, by the way. And if you're working in ergonomics, you've got to read this paper. Is that high quality ergonomics involves the systems approach. So thinking about the whole process of work, number of hours worked, breaks, overtime, other considerations. Something I didn't talk about in the case studies I showed you. Mine was not a systems approach analysis. My case studies were all focused on one tool. High quality ergonomics is design driven, engineering driven, not behavioral based. And the outcomes are performance and well-being to the outcomes that we all care about for workers. So I'm going to stop there and see if you have any questions or comments about the presentation. I think we have a few minutes for questions and answers. Thank you very much.
Questions for Dr. Rempel?
What are you doing, what are you guys doing, IP for the first you guys developed?
Why didn't we do any IP for the prototype? Because we work at a university. We do. You who work at the university and we who work at the university have an obligation as part of our job to turn in all of our ideas into the university to the Office of Technology Management or whatever you call your IP office here. And it's up to that office to decide whether or not your IP, your idea, should be patented or not. I find that the approach at the University of California is an archaic process that prevents good ideas from getting into the real world. And I don't know if the same thing is true here, but every university has a different way of dealing with IP. And we turn in these ideas to our Office of Technology Management, and they said that these were not patentable concepts because of the new changes in the patent law. And that they said, well, we found this patent from 100 years ago that shows this concept of lifting and lowering a drill. So that's in there too. So and we found another concept in the patent from some other device where there's a linear gear that forces the drill forward. So those two concepts are already they're already patents, and so therefore they couldn't patent again. So that was the primary reason, is they found some prior art. We don't think that prior art was particularly relevant, but it's really, they're driving it, and that's why. And from our standpoint, as researchers, my goal is that these interventions get out into the real world and they be used. And so having the university have a clamp on royalties and requiring licensing, it might inhibit that process. It also might not inhibit the process because it might provide one company with protection for taking that concept forward, that if successful, then they're not competed by another company. So there's different ways of thinking about the value of IP from a researcher standpoint. Sorry about the long response.
On that side-mounted drill, you mentioned the noise levels at 125 dB, I think. Did you think about putting a sound curtain around that as well? Is that something that
It's hard to do because the hole drilling, it's a 1 minute, and they go to the next hole in 1 minute. They're moving really fast from hole to hole, and they have to see what they're doing. But something like, we do have shrouds for capturing the silica dust. And if you move away a little bit further, you can reduce the sound somewhat. But essentially, you have to have double hearing protection for that job.
Dave, you recall who the researcher was at UC Davis that worked on the nursery project?
For which project?
The nursery twig cutting intervention.
Well, Fadi Fatala was involved with that, and I think he would be the contact who's there now. The other people who worked on that project are retired.
Thank
I can give you his email address if you
I
want.
got it, thanks.
Okay.
How often in the musculoskeletal study, how often were workers followed up for evaluation of carpal tunnel?
A good question. It varied between sites. The most frequent site, I think, was weekly from Iowa. The next one was monthly. You guys did monthly, right? And then we did quarterly, and one site did annually. So some were very frequent and some less frequent. And that was part of the problem of merging the data, there were differences in terms of the study approach from all the sites. And we had to somehow figure out how to bring that all together. John?
A couple comments. One is on the twig cutting. This might have great implications in Colorado because of the hand cutting of marijuana.
I didn't think about that.
It's really a big problem, actually, in the industry. So I'll talk with maybe Bob
Yeah.
on that. But in terms of the prospective studies that you mentioned, the results that you showed were the combined hazard ratios, because I know like Bert, who came out with the study, found that a power grip of more than 10 pounds for greater than 60% of the work cycle had a hazards ratio of nearly 20, with a confidence interval, I think 5 to almost 60. But yours, the data you presented was relatively low at 2 or 3. Was yours based upon, or what you presented, a combination of the studies rather than picking out any single one?
Yeah, ours, Sue Burt's study, which you're mentioning from NIOSH, was one of the study groups in here that contributed data to the data set. Hers contributed about, I think, 300 subjects to our study of 4,000 subjects. So it was a small part of the study sample. And Sue Burt, in her paper published in OEM, found a really nice dose-response relationship between increasing duty cycle, forceful hand grip, and increased risk. And she looked at it in a very segment-by-segment basis. Her confidence intervals are wide, and you can look along that whole stretch of duty cycle and see the confidence intervals get wider and wider. We do have some dose-response data here with, I don't know if I have it, let me see if I have it here, which shows kind of the same kind of concept. So as you go from 0% duty cycle to 80% duty cycle, you see a dose-response relationship here and 95% confidence intervals around our data. And as you get to the end here, we have less and less data in the 60 to 90% range, and so the confidence gets really wide here, and it's not really useful. But this part is very useful here. You can see that in that area where we have all our data, you see a pretty nice dose-response, relatively linear dose-response relationship, and narrower confidence intervals than Burt's study because of the sample size and the precision of measurements of the exposure.
What are the numbers in the bottom? It's 0, 20, 40,
This is percent time in forceful exertion. This is basically duty cycle of forceful exertion. And this is the hazard ratio, and that's 1.0 right here. Sorry, you can't read it. This is in the paper that with Carissa Harris Adamson is first author, published in OEM.
Stephen, you pointed out, I think, the importance of force, and yet it's the hardest variable to measure. Do you mind talking a little bit about where you think we are right now with measurement of force and where we may be heading?
I actually think repetition is hard to measure.
Please.
And force is hard to measure. They're both hard to measure. I mean, if you're measuring all repetition rates of the hand, you have to define what repetition is. When is an exertion for purposes of repetition? I think if you're just measuring hand exertions that are forceful, it's easier to measure repetition. It's easier to measure repetitive forceful hand exertions than all hand exertions, because there's so many fewer, especially if you're looking at a video. Our students, in terms of the reliability of measuring repetition rate, forceful repetition rates, and duty cycle, was pretty good. When we had the same students look at the same video side by side and do that analysis. Measuring force is really difficult, and if someone comes up with a reliable glove that you could put on for measuring grip force, it would be really, really big value for our field. A lot of people have tried, and a lot of people have failed. Because you put on a glove with sensors on the surface, and those sensors slide to the side when the person starts using their hands, or the force is applied on the side of the sensors. You just don't get a reliable measure of force. What we tried to do in this study, as you know, is estimate force by the weight of the tool, the weight of the product they're handling. We also, when we could, we directly measured the force. If they're handling a tool and they're pulling a tool, you can put a force dynamometer on that tool and you can pull it with the kind of force they would apply to whatever they're doing. So we measured force when we could with force dynamometers. And then when all else failed, we tried to do force matching. So basically, a person does their job and we have a force dynamometer next to them and they try to apply the same force here that are applying here. Force matching is okay, but I don't think the reliability is terrific. And then the group from Iowa, as John knows, they did EMG measurements. So they basically put EMG sensors on the forearm and estimated force using surface EMG. So there's a lot of different methods, none of them perfect. When you can, you are trying to measure the force with a force dynamometer right on the tool or object being handled. But it's the most important, and in some ways the most difficult thing to measure. Let me show you a slide here, though. So, I saved you from this in my presentation. I took it out. But dental hygienists suffer from wrist tendinopathies, forearm pain, and carpal tunnel syndrome because the pinch force they apply when they're cleaning your teeth, when they're scaling, is pretty high. And we put a force sensor on the tool to measure the pinch force. And when you put the force sensor on the tool, you can get a pretty reliable and accurate measurement for measuring pinch force. And in this case, we had, I think, 20 students and 20 dentists do this job of scaling on different teeth and different surfaces of the teeth, and found that students are applying around 30 to 40 newtons of pinch force. Remember, our threshold for pinch force is right around 10. So they're applying force above the threshold we're considering. And as a dentist, they apply less force. As you'd expect, they're more experienced, better quality. And, but even then, dentists are applying force at a pretty high force level too, pinch force level. So I think this is kind of as good as it gets for measuring pinch or grip forces, to instrument the tool directly and then to measure the pinch force as a person grips that tool.
I have a question about the drills that you've worked on. I can see like on a commercial construction project where there's a nicely finished concrete floor, getting those drills around is pretty straightforward, but in a mine or in maybe an outdoor setting where the ground isn't so level, I'm just kind of curious what you sort of experimented with to get the tools around to where you need them to be. You set up a track or anything like that?
I think it depends on the floor, the nature of the floor. We have different wheels for the commercial company that's taken that second idea, the big one, and they're selling them out of Richmond, California now. They've sold about 50 of them, 50 of those big drilling rigs, each about $5,000. They have different wheels. So if there's an uneven surface, they have large air-filled tires for moving over. But if it's a smooth concrete surface, they have small, hard wheels. So you pick a wheel based on the surface you're working on. But you're right, in a commercial construction sites, those really only work if the floor is relatively clean and you can move rapidly from one hole to another. But there are a lot of sites like that where you have basically, these buildings we're in right now, or the newer buildings, there's a lot of overhead drilling done to hang all of the electrical stuff and conduits overhead in these buildings. So you'd think that you'd build in systems and hangars so you wouldn't have to do that drilling, but that doesn't happen. It still doesn't happen. And we found that the overhead drilling device, as I mentioned, is really only practical if you have to do more than about 30 to 40 holes. Less than that, just do it by hand on a ladder.
Last question.
What was the average length of the cycles?
The average
8 hours of work, is that what we're talking about, the length of the shift?
for which job?
Well, I mean, the average of all.
Oh, for the study itself, they're typical work hours, about an average of 7 to 8. Yeah. We didn't take people that were part-time workers. They're all full-time workers.
Well, Dr. Rempel, we have a plaque to have you remember the day by, and we really appreciate you coming and giving us a wonderful talk. And
Yep.
I'm sure that somebody like Dr. Plazwick will want a picture, but we'll weigh your luggage down a little bit on your way back. But it's been wonderful getting a tour of ergonomics, both from the standpoint of the epidemiological as well as the intervention. So thank you so very, very much.
Thank you. Pleasure to be here. I'm around for another half hour if you have questions.